I'm going to start this last part in this position because I have a problem here that we need to work, and I don't want to just go to a full screen and back to a small screen all at the same time. We have here a hydroelectric generator at Hoover Dam, and it produces a current of 8,000 watts and a voltage of 250,000 volts. What's the power output? Well, if you look at that, that is an enormous, the power is going to be V times I, which is going to be 2.5 times 10 to the 5th volts times 8, 0 times 10 to the 3rd amps. And so you're going to have times 10 to the 9th watts produced. And 8 times 2.5 is 2.00 times 10 to the 9th watts, or 2.00 times 10 to the 6th kilowatts, if you need that number. Now, where it gets interesting is this part of the problem. Water powers the generator, enters and leaves the generator at the same velocity, but loses 160 meters of altitude. So all of the energy that produces this amount of power, all of this energy comes in the form of potential energy. So how many cubic meters of water per second are needed with 85% efficiency? Okay, so that means we start out with the power produces, or the energy is per second, so it's 2 times 10 to the 9th joules per second, which is what watts are. And that's basically going to equal mgh times 0.85, 85% efficiency. And so if we do that, m here, we can't calculate that directly. M actually is the density times the volume, okay? So this number, 2.00 times 10 to the 9th, is going to equal the density times the volume, because the density times the volume is m, times 9.8 times 160 times 0.85. The density of water, we're going to assume it's fresh water. It's 1,000 kilograms per cubic meter. And so we can put that in, 1,000 kilograms per cubic meter times V is equal to times 9.8 times 160 times 0.85 equals 2.00 times 10 to the 9th. All of this, if you calculate V here, it equals 1.58 times 10 to the 3rd cubic meters per second. That's why when you have these kind of power plants, you're looking at a waterfall. Hoover Dam is an enormous waterfall. An enormous amount of water comes over every second. Now, the current, when it's produced, it can actually be produced in two forms. One form is called direct current, direct DC voltage and current that are constant throughout once the current is established, and this is shown here in diagram A. You have a constant current and a constant voltage. Alternating current, which is shown in B, oscillates. The graph shows what it looks like if you have a 60 hertz, that's 60 cycles per second, oscillating, alternating current. And what you have is a sinusoidal peak and trough, and both the current and the voltage peak and trough together, so they're in phase. Here's another diagram showing that you have both a maximum and a minimum voltage, and this is designated V subscript 0. The potential difference V between the terminals of an AC current source fluctuates in a way shown in this diagram. the expression for V at any time is equal to V0 sine 2 pi f times t. Now, V and I multiplied together equals P. So the power also oscillates. So AC power changes as a function of time. And since both the voltage and the current are in phase, the product is never negative, and it fluctuates between 0 and a maximum of I0, V0. And the average is halfway between the two. Now, something called the root mean square of the current is not the same as the average, but it's close to the same as the average, and it's equal to the maximum divided by the square root of 2. The voltage is the same. The voltage is the maximum voltage divided by the square root of 2. The average power is going to be equal to the root mean square of the current times the root mean square of the voltage. So, if we do it this way, it says what is the value of the peak voltage? What is the value of peak voltage if the root mean square voltage is 120 volts? Okay, when they give you a number, they're telling you the root mean square unless they say it's the peak voltage. And then it also says what's the peak power consumption rate if you have a 60 watt AC light bulb. So let's take a look at how we would do that. We know that the root mean square voltage is 120 volts. We also know that the average power is 60 watts. The root mean square voltage is equal to the maximum voltage divided by the square root of 2. And so that means the maximum is going to equal 120 times the square root of 2, or approximately 170 volts. We also know that P0, the maximum power, is equal to the maximum amperage or current times the maximum voltage. We know that the average power is equal to the maximum, and so 2 times the average is going to equal the maximum, and 2 times 60 is 120. Now let's end up this section and these lectures talking a little bit about electrical hazards. One of the most important electrical hazards is called a short circuit, shown here in the top diagram with this little r. And basically what that represents is an alternative path that the charges can take that's not part of the plan. And it's shown, B shows the schematic diagram of this short circuit. And because when this occurs, electrons run into each other, positive charges run into each other, and it generates an enormous amount of heat. And so you see situations where the wires touch each other and then there's a fire. So here's a device, that's used to prevent this from happening. It's called a fuse. A fuse has a metal strip with a low melting point, so that if excessive heat occurs because of a short circuit or because of excessive current, then it breaks the connection and the flow stops. So if you look at the top diagram, you see the little strip labeled metal having a low melting point. That's inside the fuse. And then you can view it from the outside, and then this is hooked into the circuit, and if the flow becomes too high, it breaks the circuit. Now B is a different kind of circuit breaker. It's one of those ones like the switches that are inside your circuit box. And basically what happens is that when the excess occurs, it causes an expansion based on the heat, and that moves the metal strip and flips the switch, as you were. So you put a fuse, and it's shown here schematically. You put a fuse into the circuit to break the circuit in case something happens. And then a person can come along and either change the mechanical fuse, or they can flip the switch. And those fuses are rated to allow a certain amount of flow. And if the flow goes over that, and this is frequently, fuses are labeled in terms of amps. If the flow goes beyond that, then you'll break the circuit. Now, people are sensitive to electrical current, and as it turns out, people are more sensitive to alternate current as opposed to direct current. So an electrical current, when it hits a person, can cause a muscular contraction. So one of the results of the muscular contraction is that the person is thrown from the electrical source. And this is not a voluntary move, it's involuntary muscle contraction caused by the electrical current. The other thing can happen is the person can be unable to let go of the wire, and this is caused by the muscles in the arms are clamped down by the electrical current, and they basically the hand grabs it and it cannot open because of the electrical current.